Hello everybody, welcome to Unit 4 of Chemistry, the best subject. So first let's start off with the electromagnetic spectrum. So the electromagnetic spectrum has these things called electromagnetic waves. And when you go across the spectrum, you see the waves are getting smaller and smaller and smaller. This means they're having more energy. Energy increases as you go across the electromagnetic spectrum. These are called wavelengths. The wavelengths are shorter as you go across the electromagnetic spectrum, and these little humps are determined by frequency. More wavelength equals less frequency. Less frequency equals less energy. So, the shorter a wavelength is, the more frequency it has, and the more energy it has. So, this is the order of the electromagnetic waves: radio, microwave, infrared, visible light, red to purple, ultraviolet light, X-ray, and gamma ray. Whoops. So similarly standard is RMI V UXG. Now let's discuss the Bohr model. So the Bohr model is very simple. So it's a nucleus in the center and then a bunch of shells around it. We'll talk more about these shells later. And the electrons are displaced on those shells. Alright, so let's talk about electron jumps. Electron jumps are something designed by Bohr. So an electron is just simply chilling on its shell right here. However, if you zap it with an electrical charge, it will jump up to another shell. When it jumps up to another shell, it absorbs the electrical charge. So the thing is, it needs energy to jump. It needs energy to jump. Then it falls down after it jumps and it releases energy. The less it falls down, the less energy it releases. And remember what we talked about earlier with electromagnetic waves. If it falls less, it releases less energy. So it releases a wave with less energy, such as red. Red is the least energy of visible light. If it were to fall all the way down from here, it would release like a green or blue wave. Okay, let's discuss more about electromagnetic waves. So these are some formulas that you're gonna have to know for Mr. X's test. So C equals lambda times nu. C is the speed of light, which is here. Lambda is the wavelength that will be given to you. Nu is the frequency. So the speed of light equals lambda equals wavelength times frequency. E is the energy. The energy is equal to Planck's constant, which is h, that is listed here, times nu, which is frequency. So energy is Planck's constant times frequency. This means that frequency is equal to equal to the energy divided by Planck's constant, and lambda, which is the wavelength, is equal to the speed of light divided by the frequency. Now let's discuss electron configurations. This is a very important bit of the test. So this is called orbital theory. An orbital theory goes up like this. These are the electrons. These boxes are called orbitals. Orbitals are areas where electrons are. There can be only 2 electrons per orbital. They must follow opposite directions. As you go up in each orbital, you must start low, then go up. You can't skip anything. And you must always remember this. This is the configuration. So based on this, you can write this. Let's look at an example real quick. Oh, these are also, okay, so this is the energy level, which is 1 here. So this energy level, 1 energy level is the same thing as shell. The electron shells we talked about before. This second energy level, it increases as you go on. Then these are sublevels, which also get more energy as you go on. See, 1s is least energy, 2s has a little bit more energy than 1s, 2p has more energy than 2s, but it's still in the same shell. And a sublevel S can have 2 electrons max, that's why there's only 1 square. P can have 6 electrons max, so there's 3 squares. And D can have 10 electrons max, so that'll be 5 squares. So let's take an example. Let's fill out sulfur. Sulfur has 16 electrons. Starting off, we're going to add 1 electron here, another electron here with an opposite spin. I'm going to continue doing that. And then we're going to reach here, and there's going to be 2 electrons that will have them both separate. Now the configuration is for this is 1s2. So on shell 1, sublevel S, there are 2 electrons. 2s2, shell 2, sublevel S, there are 2 electrons, and then so on and so forth. So how to find valence electrons? Rouchet was asking me about this. He's a little bit, anyways. So you just look at the last shell. You look at the first number, and that will be the greatest. The first number will be the last shell. So the last shell in sulfur is the third shell. Add all the electrons in the third shell, and you'll get 6 valence electrons, which are outer electrons. And talking about electrons, let's discuss Coulomb's law. Coulomb's law basically says that protons attract electrons. The further away an electron is, the weaker the attraction is. The more protons there are, the greater the attraction is. However, this rule is less important than the previous. Going down a group in the periodic table, the attraction will decrease, but going down a group, the attraction will decrease, meaning as you go down a group, the shells will increase. I'll discuss that later. The number of shells will increase, so the electrons will get further away, so the attraction decreases. However, across this should say period, sorry, across a period it will increase because there are more protons going across the period. Alright, discuss trends. So radius is the size of an atom, this is what I'm talking about. So the number on each row is the number of shells. 1 shell, 2 shell, 3 shell, 4 shell. The radius increases the more shells there are. Then ionization energy you need to kick out the valence electron. This follows the opposite trend of radius. As radius increases as you go down and decreases as you go across a group. Right? And ionization energy to kick out the valence electron, it increases across the whole opposite trend. It increases across the group, but decreases across down the column. So that is because the more the radius is, the less the ionization energy is. So they are inverse. They're in inverse. Electronegativity is similar to ionization energy. It's the attractive force of other electrons on other atoms. So if there's one atom, it's going to attract another, and the electron is going to be attracted to another atom. Basically, the nucleus of that other atom is trying to attract the electron of the first atom. The further away that electron is, the easier it is to attract. That's why it follows ionization energy. Finally, let's discuss the properties of elements. There are metals, which are shiny, good conductors, and high melting point. Metals are located on the left side of the periodic table. Nonmetals are the opposite. They are dull, poor conductors, and very brittle. They are located on the right side. There's this thin strip here called metalloids. They look like metals, but they behave like nonmetals. That's the end. Thank you. Bye.